In digital radiography, understanding what a pixel is only half the story. A digital image is constructed of millions of pixels, each displaying a color palette that ranges from black to white, with several intermediate shades of gray. Understanding how these colors are stored and displayed is crucial for the modern radiographer. In this presentation, I will use the term dynamic range to describe the number of gradations between two extremes, such as black and white. Before we begin our discussion of the dynamic range in pixels in a radiographic image, let us review some of the recent history of image formation. Specifically, let's compare analog film screen imaging to digital imaging. Film screen images display an infinite range of densities between the extremes of white and black. I know this is a controversial statement, but nevertheless it is accurate. Theoretically, for any change in radiation level, no matter how small, there should be a corresponding density change. The idea of infinite possibilities is the essence of most analog systems. Computers don't do infinite. Before an image can be recorded, the programmer must decide how many radiation levels will exist between the extremes of an exposure. Additionally, the programmer must also specify which radiation levels correspond to the various shades of gray. A film screen image is made up of microscopic silver crystals supported in a gelatin matrix. The more radiation striking the film, the more crystals remain in the matrix after processing. More crystals equal a darker shade of gray. DR and CR detectors are basically radiation measuring devices. The more radiation striking detector plate, the greater the number of electrons trapped in an excited state or contained in a detector element. A computer scans the plate, converts the electron charges into digital numbers. These numbers are later translated into shades of gray. X-ray film is a capture, display, and storage medium all in one package. Additionally, film requires a large amount of space to facilitate storage. Digital radiographs are captured by imaging plates, processed by computers, by a computer monitor, and stored on a hard drive or other digital media. The storage space for digital media is rather small compared to analog. Over 250,000 of radiographs takes about as much space as a toaster. Density change for film screen systems is very limited. Over or underexposure by a factor of 2 times demanded a repeat exposure. Underexposure can still require a repeat exposure for a digital system, but overexposure of 8 times or more can be corrected by most systems. This leads to concern over the mentality of using more radiation than is necessary to perform an examination. Calculating the possible number of radiation levels a particular plate can record is fairly easy if you know how. First, consult the manufacturer's specification sheet and find the number of bits per pixel specification. The bits per pixel is the key to determining the number of radiation levels a plate can record. As near as I can determine, digital plates can record radiation levels from 1/100th of a microgray to 100 micrograys at the upper limit. I do not have a lot of confidence in this range, but it's the best I can ascertain at the time. Suppose the specification for your panel is 12 bits per pixel. Take 2, raise it to the 12th power, and you'll find the value equals 4096. This means that any radiation that the plate receives will be one of 4096 values between the upper and lower limits of the imaging plate. Also, the image that is displayed on the computer screen can be one of 4096 different shades of gray between the limits of black and white. white being no radiation measured, black being the maximum value of radiation for the plate. If you want to do this calculation for yourself, your calculator needs to have an x to the y power key. If you have a Windows computer, the scientific calculator has this key. Press the 2 key, then the x to the y key. Then type the number of bits per pixel, in this case 12, then press the equals key to display your answer. It is the nature of computers to divide ranges of values in this manner. As I stated earlier, computers do not do infinite. Set ranges are required. Some common bit per pixel ranges used in radiography are 8 bits per pixel, which can record 256 different radiation levels. This value was used in early systems and is not in use today. 12 bits per pixel can record and display 4096 radiation levels, and that many shades of gray are possible. Recently, I've seen plates specify 16 bits per pixel, which ups the game to 65,536 shades of gray. Frankly, I can't visualize the difference between a 16-bit and a 12-bit image on a standard computer monitor. Whether or not a younger and experienced radiologist could see the difference on a diagnostic monitor is a totally different story. Over the years, standard computer monitors have increased the bits per pixel count from 4 bits per pixel to 24 bits per pixel at 16.7 million colors, 32 bits per pixel coming in at 4.2 billion possible colors. Whether or not the monitor can actually display this many colors or the human eye can process the variation is up for debate, but people are impressed by big numbers. So, a summary of the process that an image takes from an exposed plate to a computer display is: the imaging plate is exposed to radiation and the plate is scanned by either a laser in the case of a CR plate, or the individual detector elements are queried by the DR plate's software for radiation intensity on a per pixel basis. The computer then takes these radiation levels, converts them to pixels, and sends them to the pixel matrix displaying various shades of gray. The current values map high radiation values to black and dark shades of gray, and low to no radiation values to light shades of gray or white. The grid below represents a highly magnified upper left corner of an imaging plate, and the squares represent the individual pixels. To keep things simple, this plate has a dynamic range of 2 bits per pixel, which means it can record 4 radiation levels. 2 to the second power equals 4. Additionally, I've assigned a low-dose value to the white pixel. This assignment is completely arbitrary. The rightmost pixel is screened by thick bone and no radiation reaches the pixel. Therefore, 2 memory locations both record 0. When translated by the computer, this pixel is assigned a color value of white. The next pixel to the left is covered by thin bone and therefore receives a low amount of radiation, so the pixel records a 0 and a 1, which is translated to a digital 1. When the computer maps a density value to this pixel, it assigns a light gray color to the pixel. The second to the last pixel is covered by soft tissue and receives a moderately high amount of radiation. The 2 memory locations store a 1 and a 0, which translates to a decimal value of 2. The computer assigns a color value of dark gray to this pixel when displayed. Finally, the last pixel is not covered by any tissue at all and receives the entire dose of radiation. A value of 1 is stored in both memory locations. This corresponds to a 3 as a decimal number. So the computer monitor displays this pixel as being black. Theoretically, the more shades of gray possible on an image, the more information that image will convey. The more gradations of shades of gray, the more structures should be visible on an image. Don't expect to see much difference on your system monitors. Diagnostic monitors used by radiologists have smaller pixels, are more powerful graphics hardware, and are better able to make small differences visible. With that said, the human eye can differentiate about 30 shades of gray at a time, so adjusting the window level and window width may be necessary to appreciate all of the details in an image. More shades of gray, bits per pixel, also has an impact on the data processing end of our profession. An increase in pixel dynamic range will result in larger file sizes. Larger file sizes require more disk space for storage and more memory to manipulate the image. Larger files also mean slower computer operation and longer transmission times when moving the image from one location to another. To be fair, these problems have become less of a problem as computers have improved over time. To illustrate my point regarding visibility of detail, I will present 3 images at different pixel depths that will be apparent on any computer monitor. This first image is a lateral skull displayed at 8 bits per pixel depth, 256 shades of gray. Most would agree that the density and contrast are adequate to demonstrate structures ranging from the calvarium to the facial bones. The next image is the same lateral skull rendered at 4 bits per pixel, which translates as 16 shades of gray. It is striking the loss of visibility of detail. We know the details are there, but there is not enough shades of gray to represent them. To take this illustration to an extreme, here is that same image at 2 bits per pixel, or 4 shades of gray. Completely unacceptable. Just an outline of the skull is visible. Moving an image from the capture plate to the computer monitor takes a number of steps and translations. First, radiation levels are recorded on the imaging plate, and in some DR plates, the radiation levels are converted to digital values representing the amount of radiation recorded by that pixel. Other plates are scanned and the digital values recorded by the scanner. These digital images are transferred to the computer, corrected for optimum density and contrast, and assigned a gray value and sent to the computer display. Finally, keep in mind that the display that is part of your imaging system is far inferior to the one used by your radiologist. Technique imperfections will be more apparent to them than to you. A radiologist's diagnostic setup may include multiple screens, and each screen will range from 3 to 8 megapixels. Brightness is better controlled and the cost of the display is much more than the screens provided by your imaging system. Whereas system screens only display 1 to 2 megapixels and brightness is not uniform across the screen. Trying to view small changes is much more difficult using these monitors. This will end my presentation. Thank you for your attention.